So packet scheduling has been a classical problem in networking. It defines how to handle buffer packets on our networks, and in particular, it defines the time and the order at which we should forward those packets. So there's been a number of scheduling algorithms proposed in the last decades trying to achieve different performance objectives. Some of them try to minimize tail packet delays, some of them try to minimize flow completion time, some others try to enforce fairness between the tenants in the networks. So very recently, there's been an interesting question that has been put on the table, which is whether there exists a universal packet scheduler, meaning a scheduling algorithm that can outperform all the others and that could be used as a wildcard in any situation, in any scenario. Well, the answer for this question is no. We don't have such a universal packet scheduler, and therefore what we should do is, instead of focusing on generality, instead of focusing on trying to achieve this universal general scheduler, what we should do is to focus on flexibility, trying to build customized algorithms that outperform in the specific situations, in the specific scenarios that we want to target, and being able to dynamically select the best algorithms depending on the application requirements and the traffic demands. And that's why we need packet scheduling, programmable packet scheduling. Programmable scheduling allows operators to define new scheduling algorithms and push them onto hardware devices without need for hardware redesign. And there has been work on that, recent work on that. The first thing that we need to make scheduling programmable is an abstraction meaning a framework that allows us to represent schedulers on a common basis, and that facilitates us the design of these scheduling algorithms, but also facilitates us to push those algorithms into hardware. PIFO queues have been recently presented as an abstraction. The problem is that PIFO queues are difficult to implement on hardware. And only one hardware design has been proposed so far. We still don't have implementations. And even this hardware design has issues in deployability, in scalability, and in flexibility. So that's why in this work we asked ourselves whether it's possible to approximate PIFO queues at line rate, at scale, and on existing devices. And the answer is yes, we can actually do that, and that's why we're very happy to be here presenting SP-PIFO. SP-PIFO is a PIFO approximation that is deployable. We can implement it on today's programmable switches. It's scalable. It scales to arbitrarily large number of ranks and flows. And it's flexible. It does not require any traffic knowledge in advance. So let me take a step back and introduce first what PIFO queues are. PIFO queues allow packets to be pushed into arbitrary positions while only draining packets from the head. So these arbitrary positions are defined by packet ranks, which can just be understood as priorities. So intuitively, the smaller the rank, the higher the priority. So we can see here an example in which we have a PIFO queue with packet ranks from 1 to 5, and we have a new packet that is coming with a rank of 2. So when the new packet is received, the PIFO queue will push that packet following the relative order defined by the packet rank, in this case between packets with ranks 1 and 3. And once all the packets have been pushed, the PIFO queue will just drain the packets from the head. Now, how to make a programmable scheduler? Well, we need two pieces. The first part is a rank computation. That is where the operator can design the algorithms that define this relative order of packets through these ranks. And then we have the PIFO queue that will just execute those ranks. So here we have an example in which we receive a packet. And the first thing that we need to do is to compute the rank for that packet. And then once we have that rank, the PIFO queue will just push it following the relative order defined by this rank. And that's how the PIFO abstraction works. And what we present here is a different abstraction in which we keep the rank computation, which is the programmable part, but we substitute the PIFO queue for a set of strict priority queues and an adaptation strategy that defines how to map packet ranks to the priority queues. When the number of queues is very big, that's very easy to do. That's straightforward because we just have to map ranks to different priority queues in order of priority. And when we drain those queues, we can see how the output that we receive is exactly the same that we will obtain with an ideal PIFO. The issue is that in practice, we don't have such a big number of queues. The number of queues is limited, and it's usually smaller than the number of ranks that we have. And therefore, we have a problem, that is that ranks need to share those queues, and therefore we can have scheduling errors. We can see that with an example. In this case, we have two priority queues, and packets with ranks from 1 to 3 are mapped into the highest priority queue, and a packet with rank 4 is mapped into the lowest priority queue. We can see how when we drain these queues, we have a scheduling error between the packet ranks with rank 2 and 3, meaning that a packet with higher rank, in this case the packet with rank 3, is drained before than a packet with lower rank, which in PIFO does not occur. The good news is that we can try to minimize those scheduling errors by defining mapping strategies. So let's see first how we define mapping in SP-PIFO. Mapping is defined by using a parameter which we call Q-bounds, which are just thresholds that define that are used to define whether a packet with a certain rank can be mapped into a specific priority queue. So let's see it with this example. In this case, we have a first mapping strategy in which the queue bounds are set to 1 and 4 respectively for the higher and the lower priority queue. The mapping process, what it will do is when we receive a new packet, in this case is a packet with rank 1, we will scan all the queues from lower to higher priority, and we will check whether the rank of the new packet is bigger or equal than the queue bound. If that's the case, we will be able to enqueue that packet in that priority queue. If not, we will just continue scanning the rest of the queues. In that case, the packet with rank 1 is not bigger than the queue bound of the lower priority queue, and therefore will be enqueued in the higher priority queue. The same will happen with the packets with ranks 2 and 3 that will also be mapped into the highest priority queue. But when we receive the packet with rank 4, in this case, it will be mapped into the lower priority queue because the rank of this packet is equal to the queue bound. Now, we can see that when we drain those packets, we have a suboptimal output. It's exactly the same output sequence as we have seen in the previous slide, in which we have a scheduling error between the packets with rank 2 and 3. Now, we can define another mapping strategy in which the queue bounds are set to 1 and 3 instead of 1 and 4. And we can see that how by following this mapping strategy, the packets with ranks 1 and 2 are mapped into the higher priority queue, while the packets with ranks 3 and 4 are mapped to the lower priority queue. And when we drain those queues, we have an optimal output, so the same output sequence that we would obtain with an ideal PIFO queue. So that two examples show us that by defining different mapping strategies, we are able to optimize somehow the output of these sequences in a way that we can minimize scheduling errors. So the question is, how can we design automatically these mapping strategies that minimize scheduling errors? And that's what we will cover in the rest of the talk. So I would like to first introduce the SP-PIFO design, how SP-PIFO adapts these mapping strategies per packet dynamically. Then I would like to introduce how you can implement SP-PIFO on today's programmable switches. And finally, I would like to introduce some evaluation results. So let's go with the first part. I would like to frame the problem formally first. What we're trying to do is to find the optimal queue-bound design, which is the one that minimizes the scheduling errors across all the different ranks. So the first thing that we do, we start with queue-bound set to 0 because we don't have any traffic knowledge in advance, as we mentioned before. And we will try to build up how SP-PIFO works through an example. So in this case, we receive a packet with a rank of 4. And by following the mapping process that we have introduced, it will just be mapped into the lower priority queue because the rank is bigger than the queue bound. Now, if we do the same for the second packet, the mapping condition will also be satisfied for the lower priority queue, and the packet will be mapped into this lower priority queue. However, as you can see, when we drain that sequence, we can already see that we will have a scheduling error if we do that, because the packet with rank 4 is drained before the packet of rank 3. So let's go a step back and let's see what we would like to do differently to prevent that scheduling error. And what we would like to do different is to push that packet into the higher priority queue so that we can avoid this error from happening. So to do that, what we have to do is to increase the queue bound of the lower priority queue to the rank of the packet that has been enqueued already. In this case, we have to increase the queue bound to 4, and therefore, by following the mapping process, now the next packet, the packet with rank 3, will be mapped into the higher priority queue. As well, we have to do the same for the packet that has been enqueued now. We have a packet enqueued with rank 3, so therefore we have to increase the queue bound. So that's what we call push-up mechanism, and with this push-up mechanism, what we are doing is to push low-rank packets to higher priority queues so that we prevent scheduling errors that occur in the lower priority queues. Now let's continue with the example, and now it comes a packet with a rank 2. And as you can see here, we have a problem that is that the mapping condition is not satisfied for any of the queues. So the rank is not bigger or equal than any of the queue bounds, and that's because we don't have more queues. So ideally, we would like to continue the mapping process in the higher priority queues, but we don't have such a number of queues. Therefore, we have only one option, that is enqueuing that packet. We cannot prevent the scheduling error. What we can do, however, is to learn from that scheduling error and try to prevent that error from happening again in the future. And to do that, what we have to do is to decrease the queue bounds so that future packets that come with a rank of 3 in this case will be mapped into the lower priority queue, and we will avoid that errors from happening. To do that, what we do is we compute the cost of this error, that is basically the difference between the packet rank, the small packet rank that we have just enqueued, and the queue bound, which keeps track of the highest rank in the queue. And we decrease this value from all the queue bounds. So we decrease it for the highest priority queue, and we decrease it for the lowest priority queue. And you can see how now, when the next packet comes, the packet with rank 3 will be mapped into a lower priority queue. So SP-PIFO adapts per packet with these two different mechanisms, the push up that pushes low rank packets to higher priority queues, and the push down mechanism that pushes high rank packets to lower priority queues. By doing that, we can distribute the packet ranks across the priority queues with a very simple mechanism in a way that we minimize scheduling errors. Now let's see how we can implement SP-PIFO on programmable switches. We have to focus on the ingress part of those programmable switches, and we will have to do 3 different things. The first is just a configuration step. We just have to set the traffic manager to support a set of priority queues. And the second thing that we need is to keep track of these queue bounds that we have defined. And to do that, we need to set 1 register per queue bound, which is 1 register per queue. And it's important that we need to keep those in sequential stages on the pipeline so that they can be accessed sequentially during the mapping process. The third thing that we need is metadata to tell the traffic manager which is the queue that has been selected for the packet that we are processing. And we will also need extra metadata to tell the traffic manager the cost of the scheduling errors in case we detect one. And that's in order to implement the push down. Remember that when there's the push down, we have to update all the queue bounds. So since we have already accessed all the registers when doing the mapping process, and we cannot access these registers again in the pipeline, what we have to do is to resubmit the packet so that we can access the registers again and update the queue bounds accordingly. So that's for the implementation, and let's see some evaluation results. The question we want to answer here is to see how does SP-PIFO approximate widely known scheduling objectives. In this case, we choose 2 very different scheduling objectives that are minimizing flow completion time, which we will focus on pFabric, implementing pFabric on top of SP-PIFO, and enforcing fairness. We will run a fluid model of a start time fair queuing on top of SP-PIFO and see how it performs. So we do packet level simulations that they have been implemented on top of NetBench, which is a packet level simulator that was developed at ETH. We use a leaf spine topology with 144 switches, links of 1 and 4 gigs per second, and we use widely known traffic distributions, the web search, and the data mining from the pFabric work. So first, let's see in flow completion time. As mentioned, what we will do is to implement the ranking algorithm defined by pFabric in top of SP-PIFO, which is our proposal, in top of the ideal PIFO in case we had that one, and we just compare with DCTCP and TCP with drop-tail queues just for comparison as a baseline. So we check the flow completion time of small flows in the 99th percentile and of big flows on average, and we can see how SP-PIFO performs very close to the ideal PIFO and also quite better than the baseline. So now for the fair queuing, we do exactly the same. Now we implement a ranking algorithm that is following this fair queuing scheme, and we compare to the ideal case in which this fluid scheme is implemented in the ideal PIFO, and also with the state of the art, which is approximated fair queuing. And we analyze instantaneous fairness by checking the flow completion time of the small flows, and also the split, the flow completion time across all the different flows of all the different sizes. And we can again see how SP-PIFO approximates the ideal case quite closely and also is very close from the state of the art. To finish, I would just like to encourage you to check our website. You will see extended evaluation also on hardware. You will also see, we will discuss the future steps and some of the limitations of our proposal, and all our code is publicly available and all the experiments are fully reproducible. So with that, I would like to conclude my talk by saying that today we've learned how to make scheduling programmable in at line rate, at scale, and on existing devices. SP-PIFO does so by adapting the mapping of packet ranks to priority queues, and it does not require any traffic knowledge in advance. So that's everything from my side. Thank you very much, and I will be very happy to take questions.
So hello, this is Danny Chen from Princeton University. Thanks very much for the great talk and the brilliant idea. I have a question about, do you have any bound on how many recirculations or resubmits you need? And what's the relationship between that bound and the number of queues?
Yes, so we have, you will see in the paper that we have a section which is SP-PIFO behavior characterization, in which we compute the number of inversions that we can have for different traffic distributions. And the issue is that then once you know the number of inversions that you can have, or scheduling errors as we call them, you need to know how this translates to performance. And that's also why then we make this performance evaluation in which we check how does it affect in the real case, in the real scenarios. And we see that it's quite close from the optimal.
But do you know how much it scale with number of queues? Like if you double the amount of queues, like how fewer inversions do you have?
We also perform these experiments on the paper. So you can also see how does it affect if we have 8 queues, 16 queues, 32 queues, and so on. And you can see that, of course, like the higher the number of queues, the lower the number of inversions that we have.
Thanks.
Sure. Thanks.
Hi, Brent Stevens, the University of Illinois at Chicago. My question is, have you considered how this scales out to multiple pipeline switches? Particular concern that there is a sharing of state that is not available between these pipelines, and if you have any solution to this problem.
So I don't know if I fully understood the question, but so we assume that we have a fixed number of state that we can use per port, let's say, and then of course we will be restricted by the number of state that we have. But the insight is that the state that we need is just like 1 register per queue. So if you use like 8 queues, you will just need 8 registers.
Yeah, so the limitation here is that packets on different input ports might go through different pipelines and thus might not have access to the same state. And so that's a limitation you should maybe consider.
Mm-hmm. Okay, thanks.
I'm Cornell. So in the evaluation sections, you basically implement P-fabric using SP-PIFO.
Mm-hmm.
I wonder how the performance will look like if we just use a naive approach. Like, let's say we have n priorities, and then we have 8 queues.
Mm-hmm.
So we just do the n divided by 8. So each queue will get n divided by 8 priorities. So how does the performance will look like if we use that approach?
So if we use a fixed distribution, you mean instead of adaptive?
Yes.
So actually, that's something that was even discussed in the original P-fabric work in the deployment section of the. Well, first of all, I would like to mention that we only implement the P-fabric scheduling scheme, so we don't implement the rate part, and we also don't implement the starvation prevention. Having said that, in the original P-fabric work, they were already suggesting that you can approximate P-fabric by using different strict priorities. However, the issue is that how to set the thresholds in an optimal way is very difficult. And it's very difficult because it actually depends on the traffic distribution that you receive. So you cannot just put static thresholds. And it does not only depend on the traffic distribution that you see as a switch, but it also might evolve on time on the same switch. So it might be different across different switches, and it might be different on time in the same switch. So setting those optimal thresholds is very difficult, and that's something that SP-PIFO is solving. So we are putting these thresholds automatically, so we are making the task easier and in a transparent way for the operator. So.
Okay, cool, thank you.
Mm-hmm, thanks.
So I have a couple of questions. So
yes.
Going back to the PIFO paper, they talk about a hierarchy of PIFO queues where
Mm-hmm.
lower nodes in the hierarchy NQ
Yes.
point us to children, right? So how do you support hierarchies? It seems almost impossible to do that with priority queues.
Exactly. That's a really good question. It's something that we discuss in the paper. Actually, we have not looked at how to implement hierarchical scheduling algorithms by implementing, for instance, hierarchies or trees of PIFOs. However, you could try to do that, or either by distributing the different hierarchies on multiple switches on the path in case you have congestion, but that's a bit difficult. But what you could do is to just distribute or recirculate packets so that you can cross like the PIFO queue multiple times, or even have multiple SP-PIFOs instances in different ports, but that will be at the expense of having less memory available. So dedicating specific ports to have more stages and therefore be able to run multiple SP-PIFOs simultaneously.
I'll just note that that may violate your approximation bounds even more.
Exactly, yeah.
But anyway, so we have time for maybe one or two quick questions.
So it's like a protocol agnostic, or do you like have some queues for specific protocols?
No, it's completely protocol agnostic. So the idea is that we wanted to minimize scheduling errors across any ranks. So we do not prioritize or reduce the scheduling errors in some priority queues more than in the other. So we just want to kind of reduce all the scheduling errors evenly across all the different priority queues. Therefore, it's rank computation agnostic. So it will perform, it's a general approach instead of a dedicated one, so that you can run any ranking computation that you want, and then it will perform in all of them as well. However, it's true that if you have very clear which is the ranking computation that you want to perform, you can adapt even the SP-PIFO behavior to minimize the scheduling errors for that particular ranking computation algorithm that you have built. However, this is out of our objective, which was just providing this generality, like being able to support multiple rank computations algorithms and being able to make scheduling programmable for any possible algorithm instead of focusing on one.
All right, thank you.
Yep.
Question? Okay, very quick question. We're almost at the end of the session.
Yep.
So currently you're considering all scheduling errors to be equivalent. I was just wondering if like different scheduling errors would have different costs. Like let's say if you like give priority to like 1 instead of 2 versus 6 versus 7. Does that make sense?
I didn't understand.
So like you're trying to minimize the number of scheduling errors, but I was wondering if different scheduling errors might have different weights. In the sense that like if you're giving, if something is very high priority and you have a scheduling error on that would worsen your performance even more.
Sure, yeah, exactly. So that's what I was mentioning, that we have targeted the objective of reducing all the scheduling errors equally, regardless of where they occur, regardless on whether they are between ranks of 1 and 2, or whether they are with ranks of 100 and 101, or 100 and 110, whatever. It's true that, as I was mentioning, you could even adapt SP-PIFO to, for instance, treat preferentially the scheduling errors that occur in the highest priority queues, assuming that those packets are more important and therefore we should have more granularity. One thing that you could even do is to have, if you have a specific rank that it's for a very important traffic, you could just dedicate one queue for that specific rank and run SP-PIFO on all the other queues. So these type of adaptation mechanisms you can do, but they are for cases in which you know the traffic distribution and the rank distribution that you're working with, and our design was more focused on the generality. But still, you can do all these adaptations, yes.
Thank you.
Okay, let's thank the speaker once again.
Thank you.